All right, hi everybody. My name is Ferah Munshi, and today I'm going to address the following two questions. How do low mass galaxies populate their dark matter halo? And what is the slope and scatter of the stellar to halo mass relationship? And we had a wonderful introduction to this in that last overview talk. And the method with which I'm trying to answer these questions is using hydrodynamical simulations, in particular, the Marvel and DC Justice League suite of simulations. So this suite of simulations contains 167 high-resolution dwarf galaxies, including satellites of dwarf galaxies and satellites of the Milky Way. So there are 4 Milky Way environments included here. So let's jump in. You see in front of you the stellar to halo mass relationship for this suite of simulations. On the left, if you're looking at the screen, is the stellar to halo mass relationship at a redshift of 0. So you'll notice that there are 2 sets of symbols on there, stars and circles. Stars are satellites, circles are central. And you can see that the scatter is dominated by satellite galaxies and essentially due to satellite stripping. Now, in order to understand the intrinsic scatter of the stellar to halo mass relationship, we want to look at things in M peak space, so the maximum mass that a halo ever has over the course of its history, and that's what we're looking at on the right. So we have log M peak on the x-axis, stellar mass on the y-axis, and you can see that that significantly reduces the scatter and it gets rid of that flattening that we've all been discussing in the Google document. As you can see, we have a growing scatter, so it moves from about 0.2 dex, as we'd expect in higher masses at the classical dwarf range, but down in that ultra-faint dwarf galaxy range, our scatter increases to about 0.7 dex. For clarity, we've modeled our scatter using a log normal growing scatter model. So why do we care about scatter? Why do we care about the faint end? It's because we want to understand what the faint end of the mass function looks like. See if you could change slides. So this is predictions based on our simulations for the mass function. So I want to draw your attention first to the blue and green lines. In the blue and green lines, you're looking at if you include the scatter we predict versus if we don't include the scatter that we predict. And you can see that there's not much of a difference in terms of the slope of the faint end of the mass function, nor in terms of absolute number counts. What actually matters when you're predicting the faint end of the mass function, and that gray region is kind of in our ultra-faint dwarf galaxy range, is the occupation fraction. So how many galaxies actually host a halo? So that's what you see in the inset there. You can see that in all our different volumes, we have very different occupation fractions. And whether or not you have a high occupation fraction, so a lot of halos host a galaxy, versus a low occupation fraction, not many halos host a galaxy, really changes your predictions for both the slope and the number of ultra-faint galaxies you might predict. Thank you.
Okay, thank you. Next speaker.
Oh, okay, great. Thanks, Andrew. And hey, everyone. I'm Christoph Engler. I'm a PhD student from Heidelberg. And today I wanted to quickly talk to you about the abundance of satellites around Milky Way and Andromeda-like galaxies in TNG50. So TNG50 is the latest installment of the illustrious TNG suite of cosmological magnetohydrodynamical simulations. And it combines a soon-in-like resolution with a cosmological volume, therefore also a statistical sample. So if we're looking for Milky Way-like galaxies in TNG50, we set out with a simple cut in halo mass, so everything from 6 times 10 to the 11 to 2 times 10 to the 12 solar masses, and we require them to have a disky shape. And this leaves us with 160 Milky Way-like galaxies, for which you can see their satellite systems on the left as a satellite stellar mass function. So we define satellites as all galaxies within 300 kiloparsec of their host. And for this, we also require them to have a minimum stellar mass of 5 times 10 to the 6 solar masses. And as you can see, we have a huge diversity here. We have everything from systems with no satellites whatsoever, which are the curves below 1, up to 10, 11, 12 satellites. And next slide, please. But overall, the average median TNG50 Milky Way-like galaxy will have something like 4 satellites down to a stellar mass of 10 to the 6.9 or so, although there's a lot of scatter. Next slide, please. But we can also compare this to our local galaxies, the Milky Way and Andromeda, and although those lie in agreement with what we have in TNG50, they also mostly lie outside of our 1 sigma scatter. But that's also kind of to be expected because they both have very massive satellites, and we know that having both a large and a small Magellanic Cloud is something that makes our Milky Way kind of special. But in fact, we also have these kinds of galaxies in TNG50, and there are 10 Milky Way-like galaxies that host both an LMC and an SFC. So we actually, with a statistical sample like that, we can actually take a look at how satellite abundance correlates with different host properties. Next slide, please. And there are different ways we can go about this. We can either check the satellite stellar mass functions in different percentiles, depending on the host property we're looking at. In this case, it's the host stellar mass, or we're simply looking at the total number of satellites as a function of host stellar mass. And although there's a little bit of an overlap and a lot of scatter, there's kind of a trend. So more massive galaxies will host more satellites. But we can also extend this from the host galaxy to the host halo. And we know that stellar mass and halo mass are very tightly correlated with each other. Next slide, please. So if we switch to total halo mass, we actually see a much clearer trend in both the satellite stellar mass function as well as the total number of satellites as a function of total halo mass. So actually, more massive halos will host more satellites. And we find much clearer correlations with host halo than with host galaxy properties, not just for the mass, but in general. Thanks.
Thank you. And next.
Hi, I'm Aaron Romanowsky, faculty at San Jose State University, and we talked about ultra-diffuse galaxies. You heard an introduction on these earlier from Shani Daniele. I'll say the definition of these is a little bit arbitrary, but generically speaking, they have luminosities like dwarf galaxies and sizes like giant. When they were first recognized as this pervasive class of galaxies, there's been a lot of work from theorists on modeling these and explaining these. There's been a variety of different models for producing them for different mechanisms. And in fact, the models have been a bit too effective that they tend to overpredict UDGs and miss the population of normal compact dwarf galaxies. Similar problems to what we heard earlier from Coral Wheeler and ultra faint regime. But what I want to focus on in particular is a subclass, observationally modeled subclass of UDGs that are peculiar. They're old and alpha enhanced globular cluster-like stellar populations and actually very rich in globular clusters. This is a subset of perhaps up to half of the UDGs, and these are quenched even in the field. As far as I know, there's no model yet that explains those kind of UDGs. And so now connecting to the halos of these galaxies, the mass measurements are done to two different types of techniques. One is dynamics through the field stars integrated light spectroscopy and through satellite dynamics of globular clusters. And then the second method is using the counts of the globular cluster systems along with an empirical relation between that and halo mass to get some estimates of the halo mass. Now, of course, there's always going to be assumptions and extrapolations with these methods, but we do the best we can. And if you can go to the next slide, we can see the results. To date, this is a cartoon picture, compilation of a variety of studies, and showing where we stand now. And it looks like there are perhaps these two classes of UDGs in the stellar halo mass relation. Maybe half to majority are in this follow the standard relation of these normal dwarf low surface brightness galaxies, but there's this interesting peculiar class that I would call overmassive halos, or the equivalent would be their underluminous and stars or failed galaxies. And this implies a large scatter in the stellar halo mass relation, but this is not the scatter we've been hearing about down below 10 to the 10 stellar mass halos, but this is around 10 to the 11 regime, where it's perhaps surprising to see this kind of scatter. Is this scatter related to some other property like low surface brightness? This needs more investigation observationally, and then also raises the question of how do you get these kind of failed galaxies? It seems we need some kind of quenching mechanism at high redshift, perhaps around the time of globular cluster formation, to stop star formation permanently in these galaxies. So on the opposite end of the spectrum, besides these overmassive UDGs, there are the undermassive UDGs. And these are ones where there's two examples found so far. Again, Shani mentioned these earlier, NGC 1052 DF2 and DF4. There's been a bit of controversy, but seems to be convergence on them being very low or in dark matter, completely dark matter free, perhaps. And the vanilla explanation for these could be tidal stripping, as we've heard. Expect galaxies to move to the left in this plot as they are accreted into a massive host. Now, on these particular galaxies that are relatively massive satellites with luminous satellites that are around 100 kiloparsecs out from the host, seems to require some degree of fine-tuning in the orbits and timing to get this to work out. So that does raise the question of, are there some other mechanisms for making a galaxy without dark matter halo, shock gas, or tidal dwarfs? So I will leave it there.
Okay, thank you. Next.
Hello, my name is Kevin McCarthy. I'm a PhD candidate at the University of Utah, working with Professor Zhang Zhang. This morning, I'm going to speak with you briefly about our search for galaxy assembly bias in velocity space. Searches for galaxy assembly bias in real-world data is complicated by the need to observe galaxies that are split by some assembly-dependent variable while remaining to reside within the same host halo mass. Recently, Lin et al. 2016 observed central-only galaxies within a fixed halo mass bin, verified through measurements of the excess surface mass density from galaxy-galaxy weak lensing, results of which are shown in the bottom panel of the middle plot. They split these galaxies into early and late type samples according to specific star formation rate, with the early type in the red and the late type in the blue dots. In the top panel of the middle plot, we see the projected correlation function, along with predictions from age-matching galaxy catalogs shown in the cyan and the magenta curves. The ratio of these measurements and predictions, the green dots and the orange contours in the middle panel, do not agree, suggesting no assembly bias signal. So informed by this selection criteria, we extend the search into redshift space, the 2-point correlation function of which is shown in the right plot, adding in the line of sight direction, which is sourced from the redshift of the galaxies, where we're able to extract cosmological information from the dark matter velocity field. So by modeling the clustering multipoles, the monopole and quadrupole from this observation with the halo occupation distribution, or the HOD framework, plus the galaxy velocity bias, we can learn about the relative velocity between the central galaxy and the host halo. Specifically, we're interested to see if our early late samples have similar host halo mass but show significantly different values for the central galaxy velocity bias, a parameter that details how offset the relative velocity is between the central galaxy and the host halo. Next slide, please. So here I show you the measurements and our HOD modeling fits for the projected monopole and quadrupole 2-point correlation functions, shown in the top row from left to right. For one of our early late sample pairs, we have other selection pairs that we'll present in the publication. For both fits, the projected and the projected plus the redshift space, we find consistent mean host halo masses, which we show in the bottom left and middle plot. And with the fit to the monopole and quadrupole, we can constrain the central galaxy velocity bias, which I show you in the bottom right plot. So we find that there appears to be a split between the early and late central velocity biases. If this detection is robust, this would imply that the early systems with low specific star formation rate have their central galaxies more perturbed within their host halos than the late systems. So if these quenched low specific star formation rate early systems are more likely to be ellipticals, and the active star forming high specific star formation rate late systems are spirals, this could indicate a central velocity bias dependence on the morphology of the galaxies, or rather on the magnitude of the merger event, whether or not these systems have undergone a major merger. So that's all I have to show you. Please look for our publication archive in the very near future.
Thank you very much, Kevin. Next.
Cool. Hello, I'm Yifei Luo, and I'm a grad student at UC Santa Cruz. So after many enlightening talks about dwarf galaxies this morning, I think I don't have to say much about why we still want to study dwarfs. So I'll go directly to introduce our new Merian survey, which we will use the DCAM Blanco telescope to get a large and fairly complete sample of star-forming dwarf galaxies between 10 to the 8, 10 to the 9 solar mass in the HRC field for lensing. And our co-PIs are my advisor, Alexi Lieto at UCSC and Jenny Green at Princeton. And I also list all the other co-authors below. Next slide, please. So the idea of the Merian survey is that some new surveys such as HSC or LSST in the future are deep and wide enough to allow us to measure the weak lensing signal of dwarf galaxies down to 10 to the 8 solar mass. And HSC is actually the first wide survey which is pretty complete at 10 to the 8 solar mass at a reasonable cosmological redshift for lensing. If we could stack all those dwarf galaxies below redshift 0.25, we will get a pretty good lensing measurement. However, the problem is, although those dwarfs can be easily detected by those deep imaging surveys, they're still too faint for any SPECT survey. And for our dwarfs below redshift 0.2, the broadband photodiodes are just not good enough for lensing. Next slide, please. Here comes our Merian survey. Since nearly 90% of dwarf galaxies between 10 to the 8, 10 to the 9 solar mass are still star forming, we could use some extra filters to improve the photodiode. So we built 2 medium band filters targeting at H alpha and oxygen 3 emission lines between redshift 0.05 to 0.11 for DCAM. And this redshift range, which is also the wavelength range of filters, is optimized to ensure that it is wide enough to include a large volume of galaxies for lensing, and also narrow enough to detect the axis of the emission lines sensitively. The Merian survey would use 64 nights on DCAM, starting from February 2021 to the end of 2022. And we plan to cover more than 800 square degree in HSC wide field, hope to get a fairly complete sample of 100,000 star-forming dwarfs to do lensing. Now, our predicted lensing signal noise is about 36 out to 0.5 megaparsec, which would be a decent lensing measurement for our dwarfs. And once we have this large sample of dwarf galaxies, one can test lots of other things, such as mass size relation, or even if there's an AGN activities in those dwarfs. So I will stop here, and if you are interested in this survey, please just keep an eye on it, or just go to chat with Alexi or Jenny or anybody else on the team. I'm pretty sure we'll be happy to talk. That's all for me.
Thank you very much. Next.
All right. Hi, everybody. My name is Isaiah Santistevan. I'm a graduate student here at the University of California, Davis. I work with Andrew Wetzel using many of the fire simulations of Milky Way mass galaxies. And we recently just published a paper in MinRAS that was focused on the formation times and the building blocks of these galaxies. So one interesting takeaway from our paper is that we saw that local group-like galaxies, or galaxies in paired systems, much like the Milky Way and Andromeda, tend to form earlier than their isolated counterparts do. So if we look at this plot on the right-hand side, what I'm showing is the fractional stellar mass growth relative to its redshift 0 stellar mass as a function of redshift or look-back time. And so we had 6 isolated galaxies and 6 local group-like galaxies in our sample. But I want you to focus in on the thick dashed gray line, which represents the average stellar mass growth of a local group-like galaxy, and compare that to the thick solid gray line, which is the same for an isolated galaxy. And what you should be able to see is that the local group-like galaxies are forming any fraction of their stellar mass earlier than the isolated galaxies do at all redshifts that we looked at. So for instance, if you look at, or if you define galaxy formation based on the time that it takes a galaxy to form, for instance, 10 or 50% of its redshift 0 stellar mass, what we see is that the local group-like galaxies are forming earlier by about 1.6 to 1.8 gigayears or so. And this is consistent with other definitions that we used to define galaxy formation. So this raises the interesting question of why does this happen? And so we thought this was originally related to the dark matter halos. And so if we go to the next slide, what I'm showing here is the same kind of plot that we just looked at, except we're looking at the fractional mass growth of the dark matter halos that host these galaxies. And for redshifts greater than about 2.5 or so, what you should see is, again, the local group-like galaxies are forming their dark matter halos earlier than the isolated galaxies do. But we see that this difference tends to converge at later times. And so I think it's popular in the literature to also define galaxy formation based on the time that it takes a dark matter halo to form, for instance, 50% of its final mass, but we see that these differences between local groups and isolated systems isn't as large as it is at early times. So to first order, we think that it's this early halo formation is what's driving the differences across all redshifts between the galaxy formation in local groups and isolated systems. Thanks.
Thank you very much. Next speaker.
Hey everyone, my name is Claire Dickey. I am a graduate student finishing up at Yale working with Marla Jiha. Today I'll be sharing a very quick sneak preview of some work I've been doing with the IQ Collaboratory. Earlier this morning, Marla gave a great preview of this particular set of observations that I'm quite interested in, which is that there's the presence of a threshold for the quenching of isolated galaxies in SDSS. Basically, isolated galaxies observed in SDSS don't appear to be able to self-quench below 10 to the 9 in stellar mass. And then when the IQ Collaboratory came together, we wanted to know if simulations of galaxy evolution reproduce this key observation. And to answer that question, I developed Orchard. Next slide. Orchard is a self-consistent method for making apples-to-apples comparisons between simulations and observations. For this work, we focused on creating SDSS-like surveys from 3 large-volume hydrodynamic simulations, TNG 100, Eagle, and Simba. To do this, we create synthetic spectroscopy for all galaxies in each simulation based on FSPS. And we've characterized the SDSS noise and selection functions to create noise-added and realistically incomplete surveys from each simulation. You can see the distribution of apparent RMAG and DN4000 measured from this noise-added spectroscopy for all 3 simulations as compared to our observations from SDSS here on the right. And I want to highlight that in this case, we're interested in reproducing a particular set of observations from Jiha et al. 2012, and so we focused on SDSS as well as these large 100 megaparsec volumes. But this is a methodology that can be easily applied to both other sets of observations and surveys, as well as to other types of simulations, semi-analytic models, and zoom-ins. And I also want to say that taking the time to do this step of these mock surveys is critical for making meaningful comparisons between the observations and simulations, as there's no other way to select the corresponding isolated and quiescent population in the simulations to compare against the observations. Next slide. So here I'm showing the quiescent fraction of isolated galaxies from SDSS in black. Highlighted in the inset, you can see at about 10 to the 9 stellar mass, we no longer observe any isolated quiescent galaxies in SDSS. And you can see the 3 simulations and the derived quiescent fractions for each of them. What we find is that all 3 simulations overproduce the isolated quiescent galaxy population at low stellar mass, though of our 3 simulations, Simba does the best job of matching observations. We've found that increasing the simulation resolution does not resolve this issue, and the overproduction of these isolated quiescent galaxies persists. Finally, when we take a closer look at the population of IQ galaxies selected via the mock surveys, we see that there are different characteristic quenching timescales for each population, which suggests an exciting avenue for additional comparisons back to the observations. And stay tuned, this work will be out on the archive in the sort of week after next. Thank you very much.
Thank you, and that was perfect timing down to the second. Awesome. Next speaker.
Hi, my name is Sergio Contreras. I'm a postdoc at the Donosti International Physics Center, and in this work, we start by comparing the amount of galaxy assembly bias of 3 different mock-galaxy samples. One is an hydrodynamic simulation, the TNG 300. One is the SAGE semi-analytic model, and one a standard subhalo abundance matching. And what we find is that all models predict a different amount of galaxy assembly bias. Even more, when we look at different number densities and a different redshift, they all evolve completely different. This is why we required a empirical model with a flexible amount of galaxy assembly bias. For that, we use the subhalo abundance matching prescription and the individual bias per object. In this quantity, basically, we measure the contribution to the large-scale clustering of each of the individual subhalos. Next slide, please. So what we do is that a standard subhalo abundance matching looks like what you have to the left, where you have a a subhalo property like B peak, and in the x-axis you have a stellar mass. And we go beam by beam of B peak, taking really narrow beams, and redistribute the value of the stellar mass in function of this individual bias of the galaxies. So they can completely correlate or completely anti-correlate or something in the middle with the individual bias. We do this separately, centrals and satellites. That way, when we do a cut of a stellar mass, we always have one, the same stellar mass B peak distribution, exactly the same, we don't modify that. And second, the same satellite fraction. And with this, we can give an additional bias to our sample. Of course, we could use any other property like concentration or environment, for example. And the results are more or less what you have to the right. In the blue line, you can see the standard galaxy assembly bias signal of the subhalo abundance matching. In black and red, you have the galaxy assembly bias of the TNG300 and SAGE semi-analytic model. And in green line, we have the value of the galaxy assembly bias of our flexible model. So the takeaway message of this work is that models predict different galaxy assembly bias, so we required an empirical model with a flexible galaxy assembly bias signal. We do this by using the subhalo abundance matching and using the individual bias of the galaxies, and with that, we are able to reproduce the galaxy assembly bias of more complex models as an hydrodynamic simulation or a semi-analytic model. Thank you.
Thank you. And next, I think this is the last. Oh, no, it's not.
Hi, everyone. My name is Xiajo. I'm a postdoc at the Case Western Reserve University. So today I'm going to talk about our recent work on the galaxy assembly bias. Next slide, please. We measured this galaxy assembly bias in the same galaxy catalog, and this assembly bias can be measured as the clustering ratio of the original sample to the shuffle sample, which shuffles the galaxies in halos at a fixed halo mass. And this gives the total amount of the galaxy assembly bias in this SAM catalog. And this comes from the contribution of all the secondary halo properties. So if we want to separate the contribution from only one secondary properties, for example, the halo H, then we replace the original clustering in the ratio by the clustering of the shuffle sample, which shuffles the galaxies at both fixed mass and fixed age. And then this gives the contribution to the galaxy assembly bias only from the halo age. And this recovers 26% of the total assembly bias, which is a relatively small fraction. And this is true for other halo internal properties, for example, the concentration and the peak. And every single one of them basically gives only 20 to 30% of the total assembly bias signal. So, but if we change to the environmental properties, for example, the density, the matter density field, or the tidal anisotropy defined on different smoothing scales, and each one of them basically correspond to a very large fraction of the galaxy assembly bias. And this galaxy assembly bias is basically caused by the combination, a combined effect of the halo assembly bias and the occupancy variation, which is the occupation difference caused by the secondary properties. For example, if you have a halo in a denser region, it is more likely to host a central and have more satellites. So this is basically the cause of the galaxy assembly bias. And if we want to model the galaxy assembly bias, it is very helpful to modify the occupancy variation. Next slide, please. So here in our work, we modified the HOD, the traditional HOD model, and to allow the parameters changes linearly with the environment. So here we add another two additional parameters, the bsen and bsite, which capture this linear change. And then these two additional parameters can be fixed by fitting the assembly bias signal in the SIME catalog. And but moreover, we can also use this modified HOD model to and together with the observational data and to hopefully constrain the assembly bias signal in the real data. That's all. Thank you.
Okay, thank you very much. And I do believe that is the last talk. Sorry, the schedule online is slightly out of order compared to the slides that we just went through. So we have about, looks like 12 minutes or so for questions for any of our speakers. I see that some people have posted some questions and comments in the Google Doc, and I encourage you to keep that going. I will try to get to raised hands if you want to raise your hand and ask a question here. I'm going to keep showing my slides in case the speakers want to refer to the slides as they answer questions. So I'm not going to look at the Google Doc directly. So please raise your hand or just call out if you have permission to speak or whatever you want to do. Do we have questions for any of our speakers? Or does somebody want to prompt us based on what's in the Google Doc? We have a question. Go ahead, Neil.
Yeah, hey. So my question was for Kevin, just to follow up on the discussion Frank and you are having, you know, on the doc.
Yeah.
Yeah, like, you know, so I didn't quite follow, like, you know, so it sounds like you're saying that the central galaxies, you know, in your groups, they have a velocity dispersion on the same order as the dark matter velocity dispersion. Is that what you're saying?
So we have an HOD fit, which by itself does not account for any assembly bias. And we have the velocity bias parameters in addition to the canonical HOD parameters, which allow for the central galaxies to be offset in velocity space from the host halo. So what this does essentially is allow the central galaxies to be perturbed within the host halo. So a central galaxy velocity bias of 0 would mean that the central galaxies are at rest in the center of the halo. Something other than that would say that they're perturbed within the halo. So if you go to the next plot, please. So this bottom right panel here shows this, how significant this perturbation is. For the late, you have in the blue contours, the bottom right panel, and then in the early, you have the red contours, and these values are about, the first peak in late is about 0.1, and the peak in the early is about 0.7. So it shows that the early systems are more perturbed within their host halos. So these galaxies, central galaxies of the early systems appear to not be relaxed within their host halos.
And so do you see spatial offsets, you know, that are consistent with this velocity offsets that you're seeing?
No. So the problem is that so far, trying to detect this spatial assembly bias spatially with a projected correlation function has been inconclusive. And this may be due to systematics of your modeling or just the measurement errors. So the idea here is that in velocity space, this signal might be more prominent. A small velocity dispersion could produce actually a more significant displacement in the line of sight direction in redshift space.
Sure, you know, but I'd expect just by isotropy, that similarly in the transverse direction on the plane of the sky, we'd also see then large offsets, if this were correct.
Right, but we only have the Doppler shift in the line of sight direction.
Mm-hmm.
So this is an effect of the Doppler shift from the peculiar velocities between the galaxies.
Yeah, I understand.
There's an issue, and we were talking about here, this is supposed to be central only catalog, but there is known to be some mislabeled centrals that actually could be satellites of more massive halos. And we don't know that value. So we also perform a fit, or we don't do a fit, but we compare to the excess surface mass density to see if our fits, our modeling is consistent with that. We could also push to smaller clustering scales, but our HOD starts to fail in this quadrupole as we go to smaller scales. So that could be further indication that this HOD model is not sufficient to reproduce this measurement.
Okay. We have a couple more questions, so I'm going to try to get to those before we're out of time. So David Weinberger, I think, is next. So go ahead, David.
So just following up on that, and I think the same comment appeared in the chat. I mean, the 0.7 seems very high for, and if anything, I would have expected the blue centrals to maybe have a higher value than the red centrals. So do you think this is really what's going on, or do you think that this is covering, this is making up for something else that's not in the model?
Yeah. So there could be an issue here with fiber collision, which we've tried to correct for. We have other samples that we haven't shown here. Just the extension of the LEN was, the physicality of the clustering was in question. We tried to do a fiber collision correction. That didn't seem to do much. We have another selection which then looks similar to this, and then now I even increased this sample to include more galaxies to improve the signal to noise. So this looks to be somehow a real measurement. On average, the alpha C's of the other samples are about 0.5. So this is not so far off. The idea here would be that if these early systems are ellipticals, then they've undergone a major merger. So if you still have late type systems or spirals, they may not have encountered another massive object that has really perturbed them from where they formed. So if this is a difference between ellipticals and spirals, then maybe the reason why the early system is higher is because they've actually undergone a major merger, dark matter's collisionless, and so that dark matter is still oscillating about the central galaxy.
Thank you.
Okay. Frank, did you have a question?
Well, it was basically along those same lines. I mean, I just want to point out that, people like Johannes Lange and others have tried to put constraints of how often is it that a central galaxy, a true central galaxy, is not the brightest galaxy in its halo. And at the massive end, at the massive halo end, it can be very frequent. And I'm just wondering to what extent that could cause a misclassification of centrals, and you just identify a satellite that you think is a central, and that could, if you plug in like 50% of that sort of contamination, it could easily explain the 0.7 value that you find. And I was trying to get to how you can rule that out as an explanation.
Yeah, we like I said in the comments, we also produce the excess surface mass density profiles. And so there might be some indication here that there are satellites that are present that we're not accounting for in our measurement. But from the clustering alone, we could push to smaller scales. And from simulations, you only get this negative dip in these quadrupoles when you have very little to no satellites. So if there are satellites, it's got to be a very small percentage. But yeah, I don't know how many you would actually need to account for this. There definitely is a degeneracy between the satellites' velocities. We can up the satellite velocity bias and lower the central satellite velocity bias, for instance. So there's definitely an issue here that we're trying to resolve. We're finalizing the draft presently.
Okay, thank you. I don't see any other raised hands here. And like I said, I'm sharing my screen, so I'm not actively looking at the Google Doc right now as we speak. I'll wait a moment if somebody wants to raise their hand, maybe ask a question about one of the other Flash talks. Oh, I see a hand go up. Annalisa.
Hi. Thanks. I have a question for Claire about the quench fraction of the isolated low mass galaxies. Claire, you mentioned at some point that the differences you notice when forward modeling the simulation does not depend on resolution, but can you please elaborate on what kind of resolution test did you do? Because all the different simulations you have there are a different resolution, but also different models which treat resolution differently.
Absolutely. So in this case, we did the same measurement of the isolated quiescent fraction on the two 25 megaparsec boxes in Eagle, so the L25 reference and the L25 recal. And then we also looked at a higher resolution 25 megaparsec box from Simba. We were not able to do the same test on TNG 50, unfortunately. That would be a great thing to add in. And we found that the Eagle reference box, that was consistent with the higher resolution large volume. We saw a slight decrease in the quiescent galaxy fraction for the recal, and we actually saw an increase in the quiescent galaxy fraction in the Simba box. And so what we took away from that as well is that there's a lot of complex behavior relating to resolution here, but it's not that simply moving to higher resolution removes this population of quiescent galaxies entirely. So had we seen with every higher resolution box that the quiescent fraction drops, we would start thinking seriously that it's purely a resolution issue, but that's not what we found.
Yes, but just as an invitation, you can always do this resolution test from below, so at worse resolution. So if you by any chance can do with TNG 300, it would be very interesting to see. When we do not forward model, we do see a 5% of difference at 10 to the 9 solar masses in the central quiescent fraction between TNG 100 and TNG 300. So it would be very nice when you do the forward modeling, whether this remains, at least within the TNG model.
Fully agree, absolutely.
Thanks a lot.
Thank you.
Thank you. Maybe one last question for one of our other speakers. Anyone have one? I'll pause for one moment in case somebody raises their hand. Okay. If not, let's thank all of our Flash Talk speakers.